Section 8.1 is a review of basic integration formulas. All of the formulas that you see right here in this table, these are integration formulas that you should have memorized. I don't stress these a whole lot, the inverse trig functions, and I don't use the hyperbolic trig functions at all in this course other than give them honorable mention. When we get into later on into chapter 8, we'll learn a better way of integrating problems that look like this. It's called trigonometric substitution. It's better than just memorizing these inverse trig integrals. So I don't really require you to memorize these a lot per se, because by the time we take this next test, we will have gone over trigonometric substitution, which you'll find is a much easier, more straightforward method for integrating problems. The first example that we have is we're told to complete the square. We want to do that so that this integrand looks like one of these integral formulas that we already have memorized. And do you remember how to do completing the square? Maybe it would be helpful if I write down the steps for completing the square. If we have our quadratic expression written ax squared plus bx plus c, you want to make the leading coefficient 1. So the first thing that I need to do is factor a negative out of this. So we're going to do some scratch work here as we go along. So 8x minus x squared I could rewrite as negative x squared minus 8x. The next thing you want to do then is add half of b squared so that you can factor the remaining quadratic into a perfect square of sums or differences. What is b in this particular problem? Negative 8. B is what x is being multiplied by. So for this particular problem, that's just negative 8. What's half of negative 8? Negative 4. And when I square negative 4, I get 16. Now what in essence I've done is I've added a negative 16 here. Do you see? Because of that negative outside. To zero that out, then, to offset it, I need to come out here and add. That's 1 over b squared. It's Monday, right? Yes. So I take half of b. Let's write it like that. B squared. So we're going to add half of b squared, then subtract the same quantity, since we're doing this all on the same side of the equation. That way we have a net change of 0. We can't change the value of this original expression. We can only manipulate the way that it looks, and that's what we're doing here. We're just manipulating the way that it looks. This is indeed equal to this amount right here in value. The next thing that we do is we factor the quadratic expression into x plus b over 2 squared. Over here then, that means that I can factor my quadratic expression into x minus 4 squared plus 16. What I have written in green are just the steps for completing the square. Now I'm going to rewrite this integral, rewrite my problem, and then solve it. So the problem originally is the integral of dx over the square root of 8x minus x squared. Based on the work that I did for completing the square, I can now rewrite this as the integral of dx over the square root of 16 minus x minus 4 quantity squared. Now if you look at your table of integrals, which one of these formulas does that problem look like? We have dx over the square root of 16 is 4 squared, isn't it? So that's a squared minus a function of x squared. A squared minus a function of x squared. Doesn't that look like sine inverse? Let's write it like this. I'm going to write it with u's and du's. And this is sine inverse x u over a. Using the number 18 right here, I've got this pattern right here. This looks very similar to that, where a is equal to what? No, a is equal to 4. What is u going to be equal to? Not negative x minus 4, just x minus 4. What's du equal to then? If I take the derivative of this, I just get dx, right? So that means putting all this together and looking at this pattern right here, this integral is going to be equal to what? sine inverse x minus 4 over 4 plus c. Don't forget the plus c on your indefinite integrals. The second exam covers just different integration techniques. So we'll be integrating. Anytime you have an indefinite integral, an integral without the bounds, you have to put plus c. Several of you lost points for that on your first test, even after I told you I was going to take points off. I know what you mean, and I know you know it's there, but you've got to write it down. If you guys want to be engineers, you've got to start paying attention to detail. It's very important. Alright, example 2. We're told to evaluate this integral, and this is a rather complicated trigonometric expression that we have for the integrand. Whenever you have an integral that has complicated trig expressions, you may have to manipulate things. You may have to multiply by conjugates or look for formulas that you can use on your identities you can use on your trig formula sheet to rewrite the integrand. I've gone ahead and identified the trig identity that we'll use here. We'll be using either the sum or the difference for sine or cosine. Looking at what we have right here, which one of these do you think this will be? It'll be sine because we have cosine sine plus sine cosine. Cosine sine plus sine cosine. On the cosine sum and difference formulas, we have the same trig functions multiplied together. Do you see that? Will this be a plus or a minus that's in between these angles? Well, if we have plus here, we're going to put a plus here. With cosine, notice it's the opposite. How will I be able to rewrite this integral then? We have this integral will be equal to the integral of sine what? Sine x plus 2x. That's then equal to the integral of sine what? 3x. By the way, even when you're doing your work on your test, you've got to put the dx in every step along the way. Don't ever write an integral on your test without telling me what the variable of integration is. So the integral of sine 3x. Can we just write our answer out, or do y'all want to see the u substitution on how we solve this? You know what, since I'm doing this for the video, we're going to do the u substitution. What would we let u be equal to? What is du equal to? 3dx. I don't have a 3dx, so I've got 1/3 du equals dx. When I write this then in terms of u, I end up with 1/3 the integral of sine u du. And what is the integral of sine? Negative cosine. So this will be equal to negative 1/3 cosine u plus c. And this is another mistake that I saw in your exams. People that used u substitutions left their final answer in terms of u when there were no bounds on the integral. You can't ever do that. If there's no bounds on the integral where you can change the bounds based on the u and evaluate and get a single numerical answer, you've got to go back to your original variable when you write your final answer. The final answer here then would be negative 1/3 cosine 3x plus c. Do you understand what I mean by you've got to go back to the original variable if there's no bounds on the problem? Y'all know this, or at least you knew it at one point. I'm just reminding you of that. That's a costly, careless mistake. Example 3 now, we have a definite integral, which is good, but we have an expression here that I don't know how to simplify. If I did a u substitution here and let u be 1 minus sine x, my du would need a cosine x in it, wouldn't it? And I don't have a cosine here. What we do in this situation is we use algebra and trig identities to rewrite the integrand. I'm going to come down here then and do some scratch work. Right now my integrand is 1 over 1 minus sine x. If I were to multiply both the numerator and the denominator by 1 plus sine x, what would I have? I would have a Pythagorean identity in the denominator. This is 1 minus sine squared x. The Pythagorean identity for sine and cosine is sine squared plus cosine squared equals 1. If I were to subtract sine squared from both sides of this equation, 1 minus sine squared would be equal to what? Cosine squared. So I'm going to say this is 1 plus sine x over cosine squared x. Because there's a single expression in the denominator, I can distribute that denominator and rewrite this as 1 over cosine squared x plus sine x over cosine squared x. But my cosine squared x I'm going to write like this. Do you agree that cosine x times cosine x is cosine squared x, and this is a valid way to write this expression? All I've done is I've distributed this denominator and put 1 over cosine squared plus sine over cosine squared. There's my sine over my cosine squared. This, using trig identities, then can be rewritten as secant squared x plus tangent x secant x. Using this scratch work, then, I can rewrite my original problem and say that the integral from 0 to pi over 4 of dx over 1 minus sine x is equivalent to the integral from 0 to pi over 4 of secant squared x plus secant x tangent x dx. You can distribute an integral. Question? You can do that. It'll still work. The statement was, at this point, this gentleman would not have separated this out like this. He would have left that cosine squared and then done a u substitution and let u be equal to sine x. Let u be equal to cosine x, and then du would have the sine x in it, and that would work. But I know that the integral of secant x tangent x is secant, so I'm going to stop there. So at this point, we've got the integral from 0 to pi over 4 of secant squared x plus secant x tan x. We know that we can integrate this a term at a time because integrals distribute across addition or subtraction. I'm not going to show that step. I'm just going to jump to the final answer. And the final answer is, what's the integral of secant squared? And then the integral of secant x tangent x is secant x. And we evaluate this from 0 to pi over 4. So I've got tangent pi over 4 plus secant pi over 4 minus tangent 0 plus secant 0. What is tangent of pi over 4? Use your trig formula sheet if you need to. This is 1 plus, what is secant pi over 4? 1. No, it's not. I'm sorry. It's square root of 2. Minus, what's tangent of 0? And secant of 0 is 1. This ends up being then 1 plus the square root of 2 minus 1. The final answer then would be the square root of 2. Any questions? Do you want to rework this problem the way you suggested at this point just to verify that we get the same answer? Probably wouldn't be a bad thing. Let's go ahead and look at that. I think it's worth taking the time to investigate. So instead of writing your your sine x over cosine squared x like this, at this point we're going to rewrite our integral as the integral from 0 to pi over 4 of secant squared plus sine x over cosine squared x. For this problem, working it this way, I am going to go ahead and distribute that integral and work these two problems individually. That's going to give me the integral from 0 to pi over 4 of secant squared x plus the integral from 0 to pi over 4 of sine x over cosine squared x. Forgot my dx. This first integral, like before, is just going to be tangent x from 0 to pi over 4, which is going to be tangent pi over 4 minus tangent 0, which is 1. And then over here I'm going to do a u substitution. Let's let u... This is the problem before. I'm just working it using a different technique. Rather than distributing the cosine in the denominator here, I'm leaving it as sine x over cosine squared x and working it just to show you that it doesn't make a difference what technique you use. You have to get the same answer. Here we're going to let u be equal to cosine x. Du then, du is equal to what? negative sine x dx. Siobhan, question? No, I let u be cosine x because then I've got the sign for my du, and then when I rewrite that, that's du over u squared. I don't have the negative there, so I'm going to rewrite this as negative du equals sine x dx. This plus then will change to a minus the integral of, are y'all okay if I just write this as u to the negative 2 du? That's going to help me with the integration. Do I leave these bounds the same when I switch to u? No, I'm going to change them. That way I don't have to go back to the original variable of x. My new lower bound, the old lower bound is 0. Cosine 0 is 1. The old upper bound was pi over 4. What's cosine of pi over 4? Square root of 2 over 2. So these will be my new bounds for u. When I integrate this, I end up with negative u to the negative 1 from 1 to root 2 over 2. You can flip your bounds if you get rid of the negative. There's two negatives here, so it's going to be a plus, so I'm going to leave it. I'm going to rewrite this as 1 plus 1 over u from 1 to root 2 over 2. And that's going to be 1 plus 1 over the square root of 2 over 2 minus 1. Now, simplifying this is where your challenge is, but it's not really that much of a challenge. The 1 and the negative 1 are going to cancel each other out, and this is going to give us, when you have a 1 over this fraction, we could rewrite that as 2 over the square root of 2, and that reduces to the square root of 2. That's 2 to the first, that's 2 to the 1/2. 1 minus 1/2 is 1/2. There's our square root of 2. It doesn't change your answer because you chose to simplify the integrand differently. The thing is, when you have these problems, you've got to manipulate the integrand using algebra and trig techniques that don't change the value of the integrand. In both of these methods, I never change the value of the integrand. This is equivalent mathematically to this expression right here, just as this expression right here is mathematically equivalent to this expression right here. Agreed? You can't change the value of the integrand. You can manipulate its appearance, though. The integral of secant x tangent x is secant x, because the derivative of secant is secant tangent. And if you look back up here at our table of identities, the integral of secant tangent is secant. This is one that you definitely want to have memorized because it comes up a lot. Moving on then to number 4. In example 4, we have an integrand that is not a proper fraction. Anytime you have an integrand that's not a proper fraction, you are able to use algebra to reduce that fraction by using long division. And that's what you want to do in this case. Anytime you have an improper fraction, you want to reduce that, unless you see another technique where u substitution or something may work easily. So we've got more scratch work. Do you remember how to do long division? Let's review it. So we have 3x squared minus 7x, and we're dividing that by 3x plus 2. This long division with algebra is just like it was with numbers in 3rd, 4th grade. You look at the first term here, divide it by the first term here. 3x squared divided by 3x is x. Then you multiply what you got up here by what's out front and subtract. Subtracting is the same thing as adding the opposite, isn't it? So rather than subtract, I'm just going to change the signs and add what I get when I multiply. So x times 3x is 3x squared. X times 2 is 2x. Once you do that, then you want to subtract. Well, subtracting, like I said, is changing the signs and adding. So when I do that, I'm left with 0 here, and negative 7x minus 2x is negative 9x. Now you look at the first term again. 3x, if I divide negative 9x by 3x, what do I get? What's left over? Then we multiply again. Negative 3 times 3x is negative 9x, and negative 3 times 2 is minus 6. Then we change our signs and add. So the negatives become positive, and typically what I do, because I don't usually do homework with two colored pens, although it would be nice if you did, you can see how using the different colors helps you keep track of the changes that you've made. I circle the signs that I'm going to be using once I've changed them so that I know that those are the right signs for adding the opposite or subtracting at this point. These terms are going to zero out, and I'm left with 6. And when we have a remainder like this, I can rewrite this then as 6 over 3x plus 2. This expression is now a proper fraction because the degree of the numerator is less than the degree of the denominator. What I do here? I take my remainder and I put it over what my divisor is. And that's what you did when you did division. Say we did long division and using numbers. Let's say that I had 23 divided by 4. Well, 4 goes into 20 5 times. 5 times 4 is 20. I subtract, my remainder is 3, and then I take my remainder and put it over my divisor, so that's 5 3/4. Does that make sense? Sometimes things are a little easier to accept in algebra if you can see how they relate to something just using arithmetic because you're more familiar with the arithmetic. So when in doubt, or if you've got a question about something, try to relate it back to a problem with just numbers and analyze the process. Don't focus on what your answer is, but analyze the process, because in mathematics, the processes are what work. Then we can dump anything we want into a problem and apply the proper process. Alright, so now I'm ready to rewrite my problem. My original problem was the integral of 3x squared minus 7x over 3x plus 2 dx. We've just shown by our scratch work that this is mathematically equivalent to the integral of x minus 3 plus 6 over 3x plus 2 dx. We can integrate this a term at a time, and I'll go ahead and rewrite this problem as the integral of x dx minus the integral of 3 dx plus the integral of 6 over 3x plus 2 dx. What do we get when we integrate x? What do we get when we integrate 3? And this, I'm going to pull the 6 out of it, and then that leaves me dx over 3x plus 2. How do I integrate this? What technique do I use? What do I let u be equal to? So what's du equal to? Do I have a 3dx? I actually do. I could take 3 out of that 6 and make it 2. This will then be equal to 1/2 x squared minus 3x plus 2, the integral of du over u. And what do you get when you integrate du over u? Natural log. Can I leave my answer like this? Nope. I've got a u in it. All my variables should be x. The final answer then is 1/2 x squared minus 3x plus the 2 natural log 3x plus 2. Do you have to solve for c? There's no way to solve for c. It's just a constant. It's an arbitrary constant that we add because we had an indefinite integral. There's no bounds on the integral. Now, this technique doesn't always work. We may be left with something over here at the end that's horrible, that we can't integrate with the skills that we have so far. We're going to learn more skills later on in Chapter 8 that we can then use to evaluate integrals that end up looking like that. For this section, though, all of your problems should be doable using these techniques. The next problem is example 5. In example 5, we're asked to evaluate the integral of 3x plus 2 over the square root of 1 minus x squared dx. Notice we have a single expression in the denominator. We can separate, or let's say this, distribute the denominator. So we're going to rewrite this integral by distributing the denominator and see if we can solve the problem that way. This will give us the integral of 3x over the square root of 1 minus x squared dx plus the integral of 2 over the square root of 1 minus x squared dx. I can pull that 2 out if I want, and over here I can do a u substitution. So we're gonna work these problems separately as if they were two separate integrals at this point. For the first integral, I'm going to do a u substitution, and I let u be equal to what? What is du equal to? Do I have a negative 2x dx? I have the x dx, so I'm going to divide both sides by negative 2, and that's going to give us our x dx here. And I'm going to number these integrals and show you and work through them separately, and then we'll put our answers together at the end. So for this first one, I can rewrite my integral as negative 3/2 the integral of du over u to the 1/2, which is negative 3/2 the integral of u to the negative 1/2 du. When I integrate this, then what am I going to get? You think it's still Monday? I have negative 3/2 times, when I add 1 to that exponent, I get 1/2, and then I divide by 1/2. That's the same thing as multiplying by 2. U to the 1/2 plus c. That simplifies then into negative 3 square root of u. But what was u equal to? Now looking at the second integral, I'm going to go ahead and pull that 2 out. We're left with 2 times the integral of dx over the square root of 1 minus x squared. We're going to have to do a u substitution here as well, aren't we? No, we don't. You're right. This is just a sine inverse because we have a constant squared minus... Yeah, we just saw this problem earlier. This is going to be equal to 2 sine inverse x plus c. I'll call that c1 and c2. Putting these two things together then, we end up with what for our final answer? And that's it. Any questions? Distributing the denominator served us well here because we ended up with two integrals that we would then take our answers and combine them to get our final answer for the problem. Not too bad. The next problem proves to be a little more problematic because I've only got one variable expression. It's got a square root, it's being cubed, and it's in the denominator. I know I'm going to have to use a u substitution. I'm going to start with my u substitution. What will I let u be equal to? And the square root of x I'm going to rewrite as x to the 1/2. Are you okay with that? When I take the derivative, I get du is equal to 1/2 x to the negative 1/2 dx. Agreed? Do I have a 1/2 x to the negative 1/2 here? No, I don't. I have a dx. What I need to do then is isolate and see what it is I'm going to plug in place of the dx. I'm going to move these two terms over with the du, so I multiply both sides by 2 and then multiply by the square root of x, and that gives me 2 square roots of x du equals dx. Problem with this is I don't like mixing my variables, x's and du's. Agreed? I need this expression to be something in terms of u. That's where I go back up to where I did my original substitution and rewrite this. What I have right now is u equals 1 plus, I don't need that dx there, 1 plus the square root of x. What is the square root of x going to be equal to then? U minus 1 equals the square root of x. This is involving some serious substituting. We're substituting within our substitution. That means then that I can rewrite my dx as 2 times u minus 1 du, and that's what I plug in place of dx. Have y'all ever seen a problem where you had to do this before? It's just remembering and thinking about doing it when the time comes. This is one of the tools that you have in your tool chest for solving these problems. You just got to be able to recall them at the time that they're needed. That's why it's easier to follow the work than it is to create it on your own whenever you're at home doing your homework problems. Rewriting the problem then, I have the integral of, in place of dx, I'm plugging in 2u minus 1 du over, and this is u cubed. I can rewrite this then. I can pull the 2 out, and I'm left with the integral of u minus 1 over u cubed du. What did we say to do when we have a single expression in the denominator and two terms in the numerator? Separate it. Let's distribute that. So that gives us 2 integral of 1 over u squared minus 1 over u cubed du. Now I'm going to rewrite this with negative exponents to make the integration easier. That gives us 2 times the integral of u to the negative 2 minus u to the negative 3 du. What do I get when I integrate u to the negative 2? This will then be plus 1/2 u to the negative 2, which I can then rewrite as negative 2 over u plus 1 over u squared plus c. Do I want to leave that as my final answer? No, I don't. I got to go back to the terms of my original variable, which was x. This ends up being, you know what, before I do that, because usually you want to get a single algebraic expression, I'm going to get a common denominator and go ahead and combine these two terms. What will my common denominator be? U squared. That means that I could rewrite this as negative 2u plus 1 over u squared plus c, which I could then rewrite as 1 minus 2u over u squared plus c. Going back to my original variable, then this would be 1 minus 2 times, gotta go back up here and see what u was equal to, 1 plus the square root of x over 1 plus the square root of x squared. And you can leave your answer like this. Honestly, I would not have counted off if you would not have written this as a single expression. If you would have left it like this, I would have been okay with that. Yes, sir.
Just at the very top, like, why did you do 1 over u squared minus 1 over u?
What I did was I distributed this denominator. U cancels with the u cubed, giving me u squared in the denominator, and that doesn't reduce, it's just 1 over u cubed. It doesn't really look like a u cubed when you look at it like that. Let me rewrite that. That better. There's one last problem for this section, and then we'll take a quick break. With this problem, there's not a whole lot that's going to help us as far as trig identities are concerned because we have just a cosine x. Later on, we're going to learn a technique, actually in the next section, called integration by parts, where we could use integration by parts to evaluate this. But whenever you have a problem in this section where you're just totally dumbfounded, what I suggest you do is go to the graph of the function or observe. Do you see the symmetry in our bounds from negative pi over 2 to pi over 2? That's an evenly spaced interval across 0, isn't it? X cubed is an odd function. Cosine x is an even function, which means that the product is going to be odd. And because of the symmetry in our bounds to the left of the y-axis and to the right of the y-axis, and the fact that this is an odd function, I'm going to have the same area under the curve or under the x-axis as I have above the x-axis. And since integrals represent areas, we know that this is going to be 0, isn't it? You may have to look at a graph though in order to be able to observe that. Let's look at a graph of this function. Make sure your calculator is in radian modes whenever you're graphing functions. We're going to set our window to go from negative pi over 2 to pi over 2. And I'll do a step at pi over 4 just so we have a tick mark. And there's no need for our y's to be what I have right here. Let's let them go from, let's say, negative 3 to 3. And then look at the graph of the function. And do you see the symmetry about the origin here? Because of the symmetry about the origin, this area right here, this negative area, is going to be exactly the same as the positive area. Therefore, this integral will be equal to 0. We use the geometry of the problem to help us out. That one's nice as long as you recognize that's what you're up against. And most of these problems, once you recognize what technique to use, none of them were really very bad, were they? Once you recognize the technique. Oftentimes I could split them apart and work them separately. The How? How do you split this one apart? We can't distribute across multiplication with integrals. We can only distribute across addition and subtraction. You've just invented a rule. You can't do that. No, then you're getting it wrong all the time. All right. All right, let's take a quick break. Let's take a 5-minute break. No, you could just graph it and you could say by graph or by symmetry.